Dear students, last time we have discussed Laplace transform, and initially we have seen that it is analogous with logarithm. Okay, so in logarithm, uh, first we apply log, and then we take anti-logarithm to get back the required result. Similarly, first we take Laplace transform of the differential equation, we get algebraic equation, and finally we need to invert back. That means we have to take inverse Laplace transform. Okay, so in this lecture we discuss all the basics of inverse Laplace transform. If Laplace transform of function f of x is given by capital F of p, then the inverse Laplace transform of right hand side function capital F of p is given by L inverse F of p equal to F of x. Okay. For example, Laplace transform of 1 is 1 upon p. This implies inverse Laplace transform of 1 upon p equal to 1. Similarly, Laplace transform of cos ax is p divided by p square plus a square. A is constant. This implies inverse Laplace transform of p divided by p square plus a square is cos ax. Next example is find inverse Laplace transform of 1 upon p raised to 4. Okay, so we have, okay, here it is 1 upon p raised to 4. There is similar kind of thing, Laplace transform of x raised to n Laplace transform of x raised to n is n factorial upon p raised to n plus 1. Okay, here there is 1 upon p raised to 4, but there is numerator is 1. Okay, so we can multiply and divide by such factor. Okay, therefore 1 upon p raised to 4 1 upon p raised to 3 plus 1. So here n is 3. And this is 1 upon 3 factorial into 3 factorial divided by p raised to 3 plus 1. So we are multiplying and dividing by 3 factorial. Okay. And this is therefore L inverse 1 upon p raised to 4 is L inverse 1 upon 3 factorial into 3 factorial p raised to 3 plus 1. By linearity, we write this as 1 upon 3 factorial into L inverse 3 factorial p raised to 3 plus 1. So this is 1 upon 3 factorial into this is x raised to 3. L inverse of n factorial upon p raised to n plus 1 is x raised to n. N is 3 here. So x raised to 3 divided by 3 factorial is the answer. Okay. So I should note that L inverse is also a linear operator. Next example. Find L inverse of 1 upon p into p minus a, where a is constant. So, okay. So such examples can be solved using partial fractions. Okay, because if it is simply 1 upon p or constant upon p, then we can find its inverse Laplace transform. Similarly, for function 1 upon p minus a or constant upon p minus a. So using partial fractions, we have 1 upon p into p minus a equal to 1 upon a into 1 upon p minus a minus 1 upon p. Okay, you need to verify this. Further, Laplace transform of x is 1 upon p and Laplace transform of e raised to x is 1 upon p minus a. Okay, therefore L inverse of 1 upon p into p minus a is same as L inverse of 1 upon a into 1 upon p minus a minus 1 upon p. And this is equal to 1 upon a into L inverse of 1 upon p minus a minus L inverse of 1 upon p. Now this is 1 upon a into L inverse of p minus a. Okay, L of e raised to x is 1 upon p minus a. So L inverse of 1 upon p minus a is e raised to ax. So this is e raised to ax minus L inverse of 1 upon p. It is simply x. Okay, L inverse of 1 upon p is x. Or this is e raised to ax minus x divided by a. Sorry, uh, L of x is not 1 upon p. L of 1 is 1 upon p, because L of x is x raised to 1. So 1 upon p square. Okay, so this should be 1. Sorry, L of 1 is 1 upon p, and so I must write here as 1. E raised to x minus 1 upon p. Homework: show that L inverse of 1 upon p square plus a square into p square plus b square is equal to 1 upon b square minus a square into sine ax divided by a minus sine bx divided by b. Next example: find inverse Laplace transform of p plus 7 divided by p square plus 2p plus 5. Solution. So here denominator is a polynomial. So we try to write it as p plus a. It is quadratic polynomial. So p plus a bracket square plus something, some b say. Okay. So we have p square plus 2p plus 5 equal to. So this is p square plus 2p. If we write this as p square plus 2p plus 4 p square plus 2p plus 1 plus 4, then this is nothing but p plus 1 bracket square plus 4, and 4 is nothing but 2 square. Okay, this is first thing. Second thing is, since we are writing in the denominator p plus 1, numerator also we try to write as p plus 1. Okay, so and we write p plus 7 as p plus 1 plus 6. Okay, therefore p plus 7 divided by p square plus 2p plus 5 equal to p plus 1 plus 6 divided by p plus 1 square plus 2 square. Okay, and this we write as p plus 1 divided by p plus 1 square plus 2 square. Okay, this is of the form p square plus a square, p divided by p square plus a square. Okay, so plus 6 we write it as 3 into 2 divided by p plus 1 square plus 2 square. Okay, so 3 is constant, this can be a divided by p square plus a square. Okay, it is not p, it is p plus 1, but we know some property which we can use. Okay, now Laplace transform of cos and sine. So this we write as 1, or instead that we write therefore L inverse of given thing, that is p plus 7 divided by p square plus 2p plus 5 equal to L inverse of p plus 1 divided by p plus 1 square plus 2 square plus 3 times L inverse of 2 divided by p plus 1 square plus 2 square. We call this as 1. Now the first term p plus 1 divided by p plus 1 square plus 2 square. Now Laplace transform of cos, here it is 2 square, so cos of 2x is, we know the formula, Laplace transform of cos of ax is p divided by p square plus a square. So it is p divided by p square plus 2 square, and the change of scale property gives L of e raised to minus x into cos of 2x equal to, so whenever we find p, we replace it by p plus 1. Okay, here it is minus 1, we write plus 1. So p plus 1 divided by p plus 1 square plus 2 square. Okay, this is change of scale. Similarly, Laplace transform of sine. Okay, so actually this means L inverse of p plus 1 upon p plus 1 square plus 2 square is nothing but e raised to minus x into cos 2x. Okay, this is number 2. This we are going to substitute in 1. Okay, the first term in 1. Now we see second term. Also, we have Laplace transform of sine 2x equal to, so Laplace transform of sine ax is a divided by p square plus a square. So it is 2 divided by p square plus 2 square, and change of scale property is L of e raised to minus x into sine 2x equal to 2 divided by p plus 1 square plus 2 square. Okay, so whenever we find p, we replace by p plus 1. Okay, so this gives inverse Laplace transform of 2 divided by p plus 1 square plus 2 square equal to e raised to minus x into sine 2x. This is 3. Now we substitute 2 and 3 in equation 1. Substituting 2 and 3 in 1, we get L inverse of, it is p plus 7 numerator divided by p square plus 2p plus 5 equal to, it is L inverse of p plus 1 upon p plus 1 square plus 2 square, that is e raised to minus x into cos 2x, e raised to minus x into cos 2x. Next, plus 3 into L inverse of 2 upon p plus 1 square plus 2 square. So plus 3 into e raised to minus x sin 2x plus 3 e raised to minus x into sin 2x. Okay, this is required solution. We can use convolution theorem to find inverse Laplace transform. Okay, so application of convolution theorem. Okay, so we have Laplace transform of f star z, that is convolution of f and z of x equal to Laplace transform of f multiplied by Laplace transform of z, that is capital F of p multiplied by capital Z of p, where capital F is Laplace transform of small f and capital Z is Laplace transform of small z. Okay. Therefore, our result is inverse Laplace transform of capital F of p multiplied by capital Z of p is f star z of x. Okay, so inverse Laplace transform converts product to convolution. Let us see example. Use convolution theorem to evaluate inverse Laplace transform of 1 upon p into p minus a. Solution. We have capital F of p equal to 1 upon p and capital Z of p equal to 1 upon p minus a. Okay. Therefore, f of x, that which is equal to inverse Laplace transform of f of p, that is L inverse of 1 upon p, that we know, that is equal to 1, and g of x, which is inverse Laplace transform of g of p, that is L inverse of 1 upon p minus a equal to e raised to ax. Okay. Therefore, L inverse of 1 upon p into p minus a equal to L inverse of f of p into z of p equal to, by convolution theorem, it is f star z of x, and this by definition is, by definition of convolution product, it is integral from 0 to x f of x minus t g of t dt, and this is integral 0 to x. F of x is 1, so f of x minus t is also 1. g of t, g of x is e raised to ax, so g of t is e raised to at dt. Now integral e raised to at is e raised to at upon a. Limits are 0 x. So this is e raised to a x minus e raised to 0 is 1 divided by a. So you can see that this answer is same as the answer we computed using partial fractions. Okay, so we can use different methods, but our answer will be the same.